So here's the setup. A particle traveling in a straight line is located at the point 6, 8, -3, and has a speed of 6 at time equal to 0. So here's what we know so far. We're not done, but I'm just let's interpret for a second. We know that the position at time equals 0. Sorry, let's write it the right way. We know the position at time equals 0 is 6, 8, -3. We don't actually know the velocity at time equals 0. We know the speed at time equals 0. So we know the magnitude of the velocity at time equals 0. So we know not that v of 0 equals 6, but that the magnitude of v of 0 equals 6. Which makes sense, right? Because if they told us what the velocity was, we should have a vector. They just gave us a value. All right. What else are we given? We're then given that where'd you go here? The particle moves towards the point (1, -9, -5) with constant acceleration. Actually, just like the last problem, right? The last problem also had constant acceleration. Our acceleration vector was -6, -6, -6, right? There weren't any variables in there. Here, the constant acceleration is a of t equal to -5, -17, -2. Which literally is just the difference between this point and that point. 6 to 1 is -5, 8 to -9 is -17, -3 to -5 is -2. So we're really seeing the difference between those 2 points to find that acceleration, which is fine. Okay, so now we want to find the r of t as a function of time. So virtually the same question. We're given the acceleration vector, we're given the initial position, but we're not actually given the initial velocity. We're given the initial speed, which is slightly different. And I will admit fully, this was really, I couldn't figure this out yesterday when I was helping a student with it. I was like, I don't know how we get the initial velocity vector until I remembered. Well, I was actually looking at something and I remembered something that's important. So this is all in the context of showing you this other thing that's important. So we're going to come back to this in just this. Yeah, well, let's start actually. Let's start working on this, and then we'll get to a point where we get stuck, and then we'll talk about this other important thing. So I'm going to do the same thing I did before. I'm going to start with my acceleration, and I'm going to anti-differentiate it. So I know that the antiderivative of acceleration is going to give me the velocity vector, and that's going to be the antiderivative of acceleration, which is going to be the antiderivative of this very unexciting constant vector, which is going to give us the vector -5t plus c1, -7t plus c2, and -2t plus c3. Sorry, it's getting kind of scrunched in there. You can zoom in a little bit. Okay. And then we would love to be able to find those constants, but we don't know v at 0. We know the velocity at 0. Or sorry, we know the speed at 0, not the velocity. So this is where things get kind of mentioned. This is where I feel like I'm going to get to a place where I'm like, oh, what do we do now? But so here, we're going to put this away for just a minute, and we're going to talk about something else real quick. So it's going away. It's coming back. Don't worry. So there are two things in this chapter that I really want to mention. And one of them is the dot product rule for derivatives. So this is like differential rules for vector functions, rule 5. The dot product rule is the following. When I think of this rule, I really just think of it, it's really just like the product rule. If you take the derivative with respect to t of two vectors, yeah, when's your next midterm? Friday? Okay, yes, we can definitely review for the next midterm. So if you take the derivative of the dot product of two vectors, it's equal to the derivative of the first vector times the second vector plus the first vector time, sorry, not times, dotted with, apologies, dotted with the derivative of the second vector. So that's thing one. Okay, that doesn't seem like too unreasonable, seems perfectly fine. Here's the other thing that comes up, which I think is pretty interesting. And this next thing is actually the thing that gets used in a lot of like, oh gosh, what was that problem? Depending on who you have for 21D, some people really kind of emphasize this a lot when you talk about like Kepler's motion and all kinds of weird stuff. Like this dot product thing, these derivatives kind of come up a lot. So later on, when you're doing 21D, think back to this on occasion. So let's say we have some vector. Let's suppose that the vector v has a constant length. Okay. In other words, the magnitude of v is a constant. So how do you calculate the magnitude of a vector? Well, it's like the sum, like you take the square root of the squares added together, right? So like, for example, like if the vector v, if I wrote v as a function of t as like v1, v2, v3, or whatever, the magnitude of v would be the square root of v1 squared plus v2 squared plus v3 squared. And then if I squared both sides, the magnitude of v of t squared would be v1 squared plus v2 squared plus v3 squared. Or another way of writing that would be the vector v dotted with itself. And that's often a substitution people make. When you take a vector dotted with itself, you say, oh, that's just equal to its length squared. So I'm going to square both sides of this. I'm going to say, well, the square of this, that's just v dot v. Right, I'm going to square both sides. So everyone is super clear on what I did. And now we're going to throw this rule at it. I'm going to take the derivative of both sides. Now, I'll remind you, the vector v itself isn't necessarily constant. An example of this, a prime example, is like the vector v of t equal to sine of ti plus cosine of tj. That vector is definitely not constant, right? It has different ij components based on what t is, but its length is constant because the point is always at the end of a circle of radius 1. So no matter where I am on that circle, the distance from the origin to that point is a length 1. So this vector has different values, but it has a constant magnitude of 1. All right, so now I'm going to take the derivative of both sides of this. Well, a constant squared is still a constant, and the derivative of a constant is 0. And on this left-hand side, the derivative of a vector dotted with another vector, well, I'm just going to use this rule right here. It's the derivative of the first vector dotted with the second vector plus the first vector dotted with the derivative of the second vector. But those two things are the same, right? Dot product order doesn't matter. Cross product order definitely matters, right? You get the negative vector if you cross things in the opposite direction, but dot product doesn't matter. So this is really 2 times v dotted with the derivative itself. Well, let's write that like that. So here's what this says. It says that the vector v dotted with its own derivative must be 0. So in other words, if v has a constant length and you dot it with its own derivative, then you get 0. I'm not saying either one of them is 0, because it's not necessarily the case, but their dot product is 0. So back to the, so questions before we move on. Okay, so back to this. Here the acceleration has a constant length. Acceleration is the derivative of velocity. But this is constant. So what that means is the dot product of the velocity and the acceleration has to be 0. So we can say the acceleration vector dotted with the velocity vector has to equal 0. You might be wondering why this is helpful. Well, we know the acceleration vector is this. And we know that the velocity vector dotted with it needs to be 0. So we can say, okay, this dot that. So now this is where I'm like, all right, now how are things going to go? I'm a little like, these have to dot to 0. So we can hopefully find the velocity vector. But here's my velocity vector. Oh yeah, okay. So now what we're going to do is we say this dotted with that has to give us 0. Yes, for sure. So because we have a vector and its derivative, and one of those things has a constant length, their dot product has to be 0. And because their dot product, and now we're going to use the fact that we know close to what each of them are to get the dot product equaling 0. And we're probably also going to have to use the fact that that this has a length of 6. Things are probably about to get a little complicated, or have already gotten a little complicated, and they're going to get more complicated. So let's see what we've got. So here's what we can say. We can say that these two things dotted equals 0. So I have that this vector, -5, -17, -2, dotted with this vector, -5t plus c1, comma, -17t plus c2, comma, -2t plus c3. That should equal 0. All right. So let's see what we've got here. This seems like it's going to get real messy. I have 25t minus 5c1. Yeah, I feel not great about this. 289t minus 17c2, and then plus 4t minus 2c3. That's supposed to equal 0. What else do we know? We also know the magnitude. Oh, well, sure. We also know that the magnitude of v of 0 should equal 6. Well, just a reminder, here's A, here's V. V of 0 is just the constants, C1, C2, C3. So we should be able to say that the magnitude of this vector is equal to 6. So that's going to imply that the square root of C1 squared plus C2 squared plus C3 squared equals 6. And then probably somehow we can put these together and get, and now I feel like things are getting out of control and I should probably cut my losses. I wanted to show you something cool. So here's what I'll say. This problem is probably worth doing, but it's probably going to get super messy and I don't want to spend your time watching me dawdle around trying to figure out what's going on. So here's what I want you to take away from this, because the thing I really wanted you to see was this previous fact here, which is that when you have a vector of constant length and you dot it with its derivative, it is equal to 0. This fact, if I had known this better when I was helping students with 21D ever, this is super important. This comes up a lot. So whether you're taking a position vector that's constant and dotting it with its velocity, which is its derivative, or taking a velocity vector being constant and dotting it with its acceleration, which is its derivative, that dot product will be 0. And that comes up often. Okay, so enough of that. I will go play with this on my own and hopefully come up with some answers for you later on, because I feel like I owe you some answers now. Well, let's move on to section 14. Chapter 14, not section. Unless there are questions. If you have questions or comments, or James, like there's something else I'd like you to talk about, happy to. Give it a minute.
Really exciting. What exactly do we use this?
That's so, I mean, so this kind of stuff actually does come up in describing like 3D motion. So people actually try to think about like how the planets and celestial bodies move, and these kinds of equations actually do play into that. I am not great at the physics, so I can't speak really well to that. The person you really should talk to is Duff. Duff knows all the physics things. He is the physics man. But these things are not just like, I'm not just talking about it because it's interesting. It's also interesting, but it actually has relevance. I'm not great at kind of speaking to the relevance though. So here, my answer is go ask someone that knows more. Chapter 14. Chapter 13 is, so I'm assuming your class has only talked about chapters section 13.1 and 13.2, nothing after that. Okay, cool. There is stuff after that. It's kind of like, it's just a bunch of formulas like take this derivative and then divide by this other thing, right? It's like a lot of stuff talking about like the curvature of things, and it's neat, but our time is limited. So let's move on to chapter 14, where we're going to talk about domain and range and all that kind of good stuff. So let's graph a paraboloid, f of xy equal to x squared plus y squared. So we're talking about graphing functions of two variables. And there's a lot of different ways to do this. Excuse me. One way is to draw the trace of each function of the function in each plane. So in 3 dimensions, there are 3 traces. Well, I should say 3 planar traces. There's one in the XY plane. So, yeah. So in the XY plane, we're going to let z equal 0. Meaning x squared plus y squared equals 0. It's not very interesting. There's only one solution, the point 0, 0. Okay. And then we have the xz plane where we let y equal 0. And that's going to get us, well, if y equals 0, I'm left with z equals x squared. Okay, that's a parabola. I know what that looks like. I should point out, in case it didn't make clear, just like in 2 dimensions, when we say like I have, for example, if I was trying to graph f of x equal to x cubed, I might think of that as y equal to x cubed. We kind of make a natural jump from f of x being replaced with y. Here we're doing the same sort of thing. We're saying, oh, f of x, y is our z. It's our other variable. It's our dependent variable. So we know that this looks like, this is my z-axis and this is my x-axis. It looks like your good old parabola. And then the same sort of thing is going to happen in the yz plane. If I let x equal 0, I'm going to get z equal to y squared. And so I'm going to get another parabola, but now in the y plane. Then we're going to try and put it all together. And so this is where you're going to want to practice your drawing skills. Some are better than others. So here's my usual X, Y, Z coordinate system. You do want to orient it this way. Technically, you can orient it different ways, but your system needs to obey what's called the right-hand rule. So I don't think we've talked about right-hand rule. Have we talked about it? We have? I can't remember. I know I've talked about it in some classes. So right-hand rule, right? Oh yeah, we definitely have. I've definitely been like, there's the corner. Yeah. So right, point your fingers in the X direction, curl them towards the Y direction, your thumb points in the Z direction. So here in the X or in the YZ plane, I have a parabola. And in the XZ plane, I also have a parabola, which is going to be a little bit hard to draw, but I can do it. And then in the XY plane, I have nothing, but if I move up a little bit, like if I look at the level curve where Z is equal to 1, I'm going to get X squared plus Y squared equal to 1, which is a circle. So up at a height of Z equal to 1, I'm getting a circle. And that's going to be true the higher I go. Right? Z equals 2. I'm going to do the circle radius square root of 2. And so we can graph this. Sorry, it's always. We can graph our paraboloid here. Like that. So this is just, we can also think of it in 21B terms. We've just taken a parabola and revolved it around an axis. Some things people might ask about this function. What's its domain? So if I look at this function, f of x, y equal to x squared plus y squared, is there anything that x and y can't be? Well, let's go back to our usual domain questions. Do I have any square roots? Definitely not. Do I have any logarithms? No. Do I have division by 0 possibly? No. So if I don't have any of those things, there are no domain restrictions. So what's my domain? So the thing I want to point out is that the domain isn't all real numbers, because we're not talking about a domain of a function of one variable. We're talking about a function of two variables. So the domain is not all real numbers, but all coordinate pairs where x or y can be any real number. So the domain for functions of two variables kind of gets a little messy. We say the domain here is the set containing all x and y, such that x and y are real. Or another way of saying this is it's the entire xy plane. Any point in the xy plane is in the domain of this function. The range, on the other hand, is all possible output values. And the output values still are just single numbers, right? They're not coordinate pairs. So looking at this function, what kind of z values can we get? In fact, I should ask, what's the smallest z value that we can get for this function? 0 is the smallest, right? It can't be negative. It can't be negative. So the range has a lowest possible value of 0, and then it does get larger and larger and larger without bound. So the range here is 0 to infinity. And for functions of multiple variables, this is always how things work. Your domain is always some set in your plane or whatever your domain is, whereas your range is just your usual kind of way of writing range as an interval. What else? Sure. Okay. Yeah, anything else about this one? No, I think that's all right. think we said the pertinent things. Let's look at, oh, where'd you go? Sorry, I've always got lots of things spread around. So let's look at another kind of pertinent graph. We're going to graph the function, yeah, f of xy equal to y squared minus x squared. And I suppose before we get started, we could talk about the domain and the range. So a lot of times you can look at domain and range without having any idea what the graph looks like. So once again, domain. Is there any restriction? No, right? The only restrictions, the only kinds of functions that really restrict the domain are the three we mentioned. Roots, I should say, even roots, logarithms, or division by zero. I will say, okay, there is a fourth category of function that has domain restrictions, inverse trig functions. But that usually doesn't pop up, so I wouldn't worry about them too much. But they could, right? So for example, the inverse sine function has a domain that's from -1 to 1. Okay. But again, it's usually not going to be in play. So here the domain, once again, is the entire xy plane. Or written more precisely, the set containing all points x comma y such that x and y are real. The range here, what are the domains with restrict? So we'll look at some examples in a minute, but the three, yeah, fair enough. I can write that down right now. So the three types of functions with domain restriction, or the three types of ways of restricting domain are: one, possible division by zero; two, square roots, or really I should say even roots. Really, because when you have an even root, you can't take the even root of a negative number, so the insides have to be non-negative. And three, logarithms. Because similar to a square root, you can't take a logarithm of a negative number or zero. So these are the three types of functions where I feel like, oh, the insides have to be careful with. Range. So for the range of this function, it would be helpful to graph it. Let's pretend I couldn't. Someone said you're not allowed to graph, it's completely illegal. I will break your hands if you graph it. Not really, I wouldn't do that. So the way I can think about the range is, well, how big could this function get? If I just pretend x is 0 for a minute, y could be anything, and this function's gonna get really, 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 really big. Right, it could be 1, 4, I mean, it could be anything really, right? I can plug in any number and get the square of it. So certainly I can get infinitely large. And then I can go the other way and say, well, what if y was 0? And then if I plug in for x, this function can get really, really negative, like as negative as I want it to get. So it looks like the range here is everything. I probably can get any real number. So the range is all reals. Let me put it to you this way. Pick a number you think I couldn't get. Or if you think I am not lying to you, name a number that you think might be hard to get to. You guys like, don't be dumb, James. Obviously you can get everything. So let's pretend I wanted to get -1,000,000, right? I was like, oh, man, like, how do I get f of xy equal to -1,000,000? Well, there's actually probably literally an infinite number of ways of doing it. But one way that would work would be to let y equal 0 and x equal 1,000. Because basically what I'm saying is this is going to equal positive y squared minus x squared. If I set y equal to 0, then I can just solve for x, and that'll work. So yes, we can get any value in the range in this particular example. How do we graph this one? Well, again, I'm going to graph some traces. So traces. The XY plane is terrible. So in the XY plane, we have, again, z equals 0. So we have y squared minus x squared equal to 0, which is y squared equal to x squared which is what? It's not just y equal to x. If we take the square root of both sides, it's actually the absolute value of y equal to the absolute value of x, which means that we have this weird kind of y equals x and y equals negative x graph. So this looks like, I want to save myself enough room to draw this thing. This looks like that, which I will tell you, it's not super obvious when you graph it. And that's your trace. In the xz plane, when y equals 0, we're going to get z equal to negative x squared. So it's going to be a downward opening parabola. And then in the yz plane, we're going to start with x equal to 0, and we're going to be left with z equal to positive y squared. So we're going to get an upward opening parabola. This is x, z, y, z. So really what I'm thinking about doing when I do this is I'm really kind of thinking about like superimposing all these on each other. So like, right, in my YZ plane, which is the board, I'm like, oh, I've got a nice parabola like that. And in the XZ plane, which is the plane chopping you, right, slicing at you, I've got this downward opening parabola like that. And then I'm not going to really think about what's happening in the XY plane because it's not super helpful. So let's try and draw this thing. And yeah, I'm going to draw like this. So here are my axes, which maybe I'll fill in a minute if I don't really want them filled in right now. And here is my nice parabola in the in the YZ plane. And then in the XZ plane, you always have to kind of give yourself the perspective, right? It's not going to be the full parabola. It's going to be tilted this way. So it's going to look narrower. So I'm going to have my parabola coming out that way and going back that way. And then supposedly you'd have the lines y equals x and y equals negative x in the xy plane. I'm not going to draw those. But here's what's going to happen. This is going to be, so no matter where I slice this, if I take other slices, like if I, let's say like, if I move over here to like y equals 2, if y equals 2, I'm going to have z equal to 4 minus x squared. So it's going to kind of be like a higher parabola. So instead of being this parabola here, it's going to be like this parabola here. Like that. And the same kind of deal over here. And then we also have a similar kind of thing happening the other way. Whereas if I, right now, it's kind of hard to see, but if I pick like x equal to 2, I've got this parabola here. You kind of see that? If I move forward, the parabola is going to move down. If x equals 2, I'm going to get z equal to y squared minus 4. So I've moved that parabola downward a bit from right there. I know it can be hard to see what's going on. But this shape is typically called a saddle. I mean, it kind of looks like a saddle, right? Someone could sit in that, like there's a horse right there. I can't draw a horse, but you can imagine a horse, right? No, not even close, right? Don't even pretend like I can draw anything. It's not a regular shape. But this shape is a saddle. And interestingly, this point here is what we call a saddle point, because it's the point where you have a minimum in one direction and a maximum in another direction. That's kind of the defining feature of a saddle. So looking back at this previous example for just 1 second, not that we're talking about this yet, but we're definitely going to be right there. We have a local minimum, right? That is definitely the lowest point on that surface. Here we have kind of a new type of critical point, a saddle point, where it's a minimum in one direction and a maximum in another direction. Okay. So yeah. You guys are still looking at that. Let me give you a moment. Yeah. Oh, sure. We'll talk. We're about to cover that more in depth. But all I was really saying here is that these are the things we have to look out for. You can't have division by zero. Oh, over here? Sure. So I was saying, so what I was saying was, if I'm trying to like draw further out, like what I'm basically doing is I'm moving over to say y equal to 2, and I know at y equals 2, I have the parabola that is z equal to 4 minus x squared, which is that downward opening parabola right there. And I would also have the same thing over here at y equals -2. I'd also have the same downward opening parabola. And then if x equals +2, I've moved forward 2. And then on this curve, I have this upward opening parabola, but it's moved down a little bit. So when x equals 2, z is going to equal y squared -4. Yeah, it was arbitrary. I was just trying to like pick something that wasn't one really. But yeah, but we're just trying to see that if you move backwards or forwards, you're still getting parabolas. They're just kind of shifting further down. So you can kind of think of like, if you move backwards or forwards, you can think of you're just kind of getting all these parabolas. They're just like down, 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 down. Whereas you move to the side, you get these downward opening parabolas. They're up, 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 up. This is chapter 14.1. In a similar way, although in an easier way, I would say, in this one, if we move up, 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 we just get larger and larger circles. Right? If you let x squared plus y squared equal larger and larger numbers, you're just going to get circles with radius equal to the square root of whatever that number is. Let's look at another example. Well, I said I was going to talk about that. Let's talk about domain for a minute, and then we'll also talk about other examples. Where'd you go? So let's look at this function here. Let's look at the function f of x comma y equals to the square root of y minus x squared. So we definitely have a domain restriction, right? We have a square root. We know we can't take square roots of negative numbers. So for the domain, we're going to start off by saying, well, all right, the stuff inside the square root has to be greater than or equal to 0. Which means y has to be greater than or equal to x squared. To me, the easiest way to understand or to visualize the domain is to actually graph it. So when I'm graphing the domain, I'm going to take my inequality, because it's usually an inequality, although not always. You can have a strict, no, it's always an inequality, really. I'm going to take this inequality and just pretend like it's an inequality. So instead of graphing y greater than or equal to, I'm going to start by graphing y equal to x squared. So graph y equal to x squared. Looks like this, good old usual y equal to x squared. And then what is almost always going to happen is one side of that function will be your entire domain in the XY plane. And the easiest way to tell is to pick a point that's on one side. So if I pick the point, say 1, 0, which is right there, does the point 1, 0 satisfy my inequality? If x is 1 and y is 0, is this inequality true? No, it's definitely not. If I plug in 0 for y and 1 for x, 0 is not bigger than or equal to 1 squared. So that point is not in my domain. Or we could have picked a point like 0, 2. And if we pick the point 0, 2 and plug it into the inequality, we can see, okay, well, now I have 2 bigger than or equal to 0 squared. Oh yeah, that checks out. 0, 2 is in the domain. So the way this works is basically once you pick a point, if it's in the domain, everything on that side of your curve is also in the domain. If you pick a point that's not in the domain, everything on the other side of the curve is in the domain. So once you've picked one point, you've figured it all out. So here's my domain. It's everything over here, including the boundary. So if I was trying to describe this, well, here's the not exciting way I would write it. I would say that my domain is the set containing all coordinates x comma y such that y is bigger than or equal to x squared. If I had to use words to describe my domain, I would say my domain is all points above and on the parabola y equal to x squared. But usually this is the way we generally describe domain, which actually in some sense I think makes it easy in that you just have to say, well, it's a set of all coordinates that satisfy whatever inequality you need to have satisfied. But there isn't a lot of like having to solve it and be like, it's this point and that point. You're just like, no, it's all these points. I do think for your visual interpretation, graphing the domain is the best thing to do because it really helps us see like, oh yeah, all these points up here are in the domain. And especially if we're going to then try and graph the 3D surface, it helps to know like, okay, well, I can only have points up here. So like when I start graphing this thing, yeah, I'll probably go to the next page actually. When I start graphing it, I'm going to have like, here's my X, here's my Y, and I know that my domain is only going to be everything that's over here. So I can only have like Z values that are above there and nothing over there. All right, let's talk about range. To me, range is always just a question of how do I think about how big this thing can be and how do I think about how small this thing can be? And often it amounts to letting one thing be 0 and asking how big or small can the function be if I let the other thing just do whatever I want to do. So if I let x equal 0 and y can be, well, y can't be anything actually. If x is 0, y has to be 0 or above, right? Because I can't have, well, no, y can't be negative, right? If x is 0, y can't be negative. But if I let x be 0, x is 0, then I have f of 0 comma y equal to the square root of y. How big can the square root of y be? Big as you want, infinite. How small can that be? What's the smallest number you get out of a square root? Yeah, definitely 0. So seeing the square root here being like the outermost thing, I know that the lowest my range is going to be is for sure at the lowest 0. It might actually be higher than that depending on what I've got inside my square root, but for sure I can't go any lower than 0. So I'm pretty confident that my range here is 0 at the lower end without bound on the upper end. But there's really, what I'm trying to say here is there's not really like a great tried and true method that always works for finding the range. It's kind of like look at what you've got and ask yourself, okay, what can I do to make it as small as possible? What can I do to make it as big as possible? Am I missing anything in between? No, great, done. Or yes, think about it, not done. Okay, so then the graphing of this. The graphing of this is, I will just fully admit, the 3D graphing has never been my forte, and I've been doing it for a long time. That doesn't mean you should, not to like cause you despair. Lots of you are probably much better drawers than me. I encourage you to give it your best shot and try to graph nice things. But for me, I'm just, it's always hard. I will also say, you young people, unlike myself, there are lots of cool 3D graphing utilities that didn't exist when I was around back taking 21C at this university. So I will just point out that before I even graph this thing, I might try, let me grab this here, 1 sec, sorry. Where are you at? I might try looking at GeoGebra and let me reshare my screen. Let's just do, yeah, that one, cool. You guys all see that on Zoom? So if I input here my function, z equal to the square root, I mean r for square root of, what we got here, a y minus x squared. So looks pretty good. So the red axis is your x-axis, the green axis is your y-axis, and the blue axis is your z-axis. So, okay, that gives us a pretty good idea of what that thing looks like. We could probably draw it. I guess we should. But you definitely, I would say, use the tools available to you to help you draw things nicely or to even just visualize what they might look like. So if I was going to try and draw this z equal to the square root of y minus x squared, I would probably draw some level curves. And so level curves means I'm just going to pick larger and larger values of z to see what happens as I move up, right? I'm really just saying, if I go higher, what's it look like in the parallel to xy plane? As I go higher, what's it look like? So what you really want to do here is you don't want to do it a bunch of times. You don't want to be like, okay, 0 equals square root of y minus x squared, 1 equal, right? It's kind of like, this is going to be silly to do this a bunch of times. Right, and here I would get y equal to x squared. Here I get square both sides, y equals x squared plus 1. Square both sides, y equals x squared plus 4. I'm getting a bunch of parabolas that are just up and up and up. So it's actually the same parabola, just shifted up, 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 or out, out, out. But I don't want you to do all this work. What I want you to do is say, okay, well, if I'm going to let my level curve be, say, z equal to c. I don't know why we use c, probably because it's a constant, but that's typically what we use. And so if I say c equals the square root of y minus x squared, and I solve this, I'm going to get c squared equal to y minus x squared. I'm going to get y equal to x squared plus c squared. So then I know that however high I am, right, however high up in the z-axis I am, my parabola is just y equal to x squared plus that height squared. So when I'm at a height of 0, it's y equals x squared. When I'm at a height of 1, it's y equals x squared. When I'm at a height of 2, it's y equals x squared plus 4. When I'm at a height of 3, it's y equals x squared plus 9. I don't have to do the work every single time to find my level curve. So then the drawing. Okay, then the drawing. He said trepidatiously. Yeah, sure. So here's my x-axis, here's my y-axis. And in the xy plane, here's my parabola. Yeah, sure. That looks all right. It looks okay. And then we're going to go up to a height of 1. So when you go to a height of 1, my new parabola is y equals x squared plus 1. So in this new plane that's at a height of 1, my parabola is going to start like here. And so I'm going to get this new parabola up there. And then at a height of 2, my parabola is going to start way over here at 4. So it's to be something like that. So we've kind of got this shape where each of these things I've drawn are what's happening. Whoops, sorry, you can't see it super well. Right, we've got this kind of thing going on where we've got like that. And again, I will say, this is why looking at the utility is really nice, because you're like, okay, well, James, you did a not terrible job of that, but I could also look at this and be like, oh, I can actually see what's going on. And so this kind of top part here is the red line I was trying to draw, but it just, my perspective is not as good as this. So use all the tools you have. Right? Yeah, just doesn't look as good as I'd like it to. Oh well. Yeah. Yeah, I guess we could extend this a little further, because so you're supposed to be seeing that like this is kind of going up and up and up. And yeah, okay, fine. Practice. I say to people while not having done lots of practice. Let's look at more questions so we can talk about domain. Because of all these things, I mean, the drawings are fun, I guess, but the domain is something that is a little more maybe easy to grasp. Maybe not, I don't know. It depends on the perspective. So let's look at this next one. Let's say our function was f of x y equal to 1 over the square root of x squared plus y squared minus 1. It is fairly common in these functions of two variables to see an x squared plus y squared pop up, or a negative x squared minus y squared, which I would encourage you to write as a minus x squared plus y squared in parentheses. X squared plus y squared together is kind of a clue. So let's talk about domain. So domain, well, I need the insides of that square root to be what? Say that one more time. Yes. Normally I would say not quite, because it has to be greater than or equal to 0. But since it's in the denominator, we know we also can't have 0. So yes, greater than 0 is exactly what we want. So then typically you want to kind of isolate the x squared plus y squared thing all by itself. So I'm going to have x squared plus y squared is greater than 1. And then I'm going to graph it because I think it's always worthwhile to graph the domain. So I'm going to graph x squared plus y squared equal to 1, which is a circle of radius 1. Now here's the thing. If someone actually asked you to graph the domain here, you would want to graph this circle as a dashed line. So I don't actually want to include the border because I don't want x squared plus y squared to equal 1. That's going to be a problem. If x squared plus y squared equals 1, I'm going to be dividing by 0. So when I draw this, if you have a strict inequality, you never want to include the border. If you have an inequality where you have a greater than or equal to or less than or equal to, then you want to include the border. Why 0 again? Because if this, well, because it has to be greater than 0 because we can't take the square root of a negative. And it can't equal 0 because if it was 0, the square root of 0 is 0, and then 1 divided by 0 is undefined. So in this case, we're going to graph this dashed like that. And then we're going to ask ourselves, okay, do we want the insides or the outsides? Well, again, pick a point. I'm going to pick, if the origin is not on the border, the origin is usually the easiest thing to pick. So pick 0, 0. Does 0, 0 work? Definitely not. 0 plus 0 is 0, which is not bigger than 1. So the origin is not in my domain, which means the entirety of the inside of the circle is not in the domain. So my domain is actually everything outside of the circle. Right, all this, there's my domain. Everything outside the circle of radius 1. Writing it, it's very not terrible. Domain can be the set containing all x comma y such that x squared plus y squared is greater than 1. So again, actually writing the domain is usually not terrible. Drawing it, thinking about what it actually is a little bit of work. Let's talk about the range. So here's where using your domain actually is going to be, I think, somewhat helpful. So if I'm thinking about the range, I know that x squared plus y squared minus 1 has to be greater than 0. I also know that, let's start with that. So then I know the square root of that also has to be greater than 0. Take the square root of something, it's positive, still positive. And then I'm going to take the reciprocal of both sides of this inequality, which might feel like kind of the wrongest thing ever, but it's okay. So when you take the reciprocal of two sides of an inequality, what happens to the inequality? Here's what I found. I'm not asking you. Oh my God, jeez. I guess I can't lift my arm up while I'm asking questions. That's ridiculous. Okay. Anyway, if 2 is less than 3 and I take the reciprocal of both sides, what do I get? 1/2 is bigger than 1/3. If you take the reciprocal of both sides of an inequality, you change the direction of the inequality. You can also think of doing the cross multiplication. And if I multiply both sides by 2 and both sides by 3, I get 2 less than 3, which makes sense. So here, I'm going to take the reciprocal of this. And I'm going to take the reciprocal of this. And what's the, I know this is not exactly precise. What's the reciprocal of 0? Yeah, it is. But really, I'm thinking if I'm a little bigger than 0, I'm a very, very small positive number. And the reciprocal of a very small positive number is a very large positive number. So essentially, if I'm a little bit bigger than 0, that means I have to be less than 50. Now, it's also true that x squared plus y squared minus 1 has to be less than infinity. Or in other words, x squared plus y squared plus 1 minus 1 can be as big as you want it to be. Right? That can be very, very, very large. Let x be really large, let y be really large. Let x be really negatively large and y be really large. When you square them, they're both going to be big. And so then, the reciprocal of infinity, that's one way you can attack this. It gets a little more challenging when you have stuff in the denominator, like, okay, well, I'm thinking about what's happening with this, but then I'm taking the reciprocal of that. So our range here is 0 to infinity. You can't ever get to 0, right? The bottom's always greater than 0, so 1 divided by that can't ever be 0. But you can certainly get infinitely large by making the denominator super duper small. For example, if x equals 1.001 and y equals 0, my denominator is going to be, well, my expression is going to be 1 over the square root of 1.001 squared minus 1, which is a very, very large number because my denominator is super close to 0. Graphing it, my favorite part. So level curves. So here's our function. And I'm going to do the thing where I'm going to say, okay, level curve, z equal to c. So I'm going to set c equal to 1 over the square root of x squared plus y squared minus 1. Now here's why it's worth thinking about the range. We know that for our level curves, our c values have to be positive because the c values are what we're setting the function equal to. They have to be in the range. So here's what we're going to do. We're going to solve this for something that makes sense. That's not very helpful. We're going to isolate the x squared plus y squared. Because basically I'm going to try and get x squared plus y squared equal to a thing and be like, oh, I have a circle. So let's reciprocal both sides. 1 over c equals the square root of x squared plus y squared minus 1. If you really aren't a fan, you could cross multiply. C times the square root of x squared plus y squared minus 1 equals 1. And then the square root of x squared plus y squared minus 1 equals 1 over c. That's also fine. It's just a longer process that way. And then square both sides. 1 over c squared equals x squared plus y squared minus 1. And finally, add 1 to both sides so that you have x squared plus y squared equal to 1 plus 1 over c squared. So here's what we've got. At z equal to c, we have a circle. Center is the origin. And the radius is the square root of that. And this is very typical for finding level curves. Like I'm just going to kind of write it as a function of c. So I know that if, well, I can't pick c equal to 0 because that's not in the domain. But if I pick, say, like c equal to, I'm going to start low. Let's say c equal to 1/2. C equals 1/2. My circle has a radius of the square root of 1 plus 1 over 1/2 squared. So 1 over 1/4, which is 4. So my radius is the square root of 5. And if c equals 1, my radius is the square root of 1 plus 1. And if c equals 2, my radius is the square root of 1 plus 1/4, which equals the square root of 5/4. So I can see that as my, oh, sorry, you can't see. We can see that as we go higher up in 3-dimensional space, my radii are getting bigger or smaller. And let's check one more value. If I plug in c equal to 4, my radius is going to be the square root of 1 plus 1 over 16, which is the square root of 16 plus 17 over 16. My insides are getting smaller, which means the square root's getting smaller. So my radii are decreasing. So as I go up and up and up, my circles are getting narrower and narrower and narrower. So it kind of looks like, and then as I go further down, like if I picked even a smaller value, like c equal to 1/10, my radius would be the square root of 1 plus 1 over 1/10 squared, which would be 1 plus 1 over 100. So the square root of 1 plus 100. That radius is just a little bit bigger than 10. So as I go lower and lower and lower, my radii are getting wider and wider and wider. So what's happening is we have something that I'm just going to draw it. Am I going to draw it? We're going to try to draw it, sure. So it's kind of doing this deal. When we go out, it's going to go, go out this way. Whenever I'm trying to draw in the x direction, I'm trying to always draw parallel to the way I've drawn the x-axis. So like I'm trying to draw this curve kind of coming down this way like that. And so we've got kind of this, I've drawn this too big. We've got kind of this thing going on here. And of course, it keeps going up as well. But you have, right, you can't draw your graph forever because otherwise you'd never stop. So this is kind of what's going on. We've got this graph that's getting narrower. Well, how narrow is it getting at the top? What's the narrowest my radius could almost get to? If I look at what I've written for my radius here, it could never really get equal to even 1, because 1 over c squared is always going to be a little bit positive, and 1 plus that will always be a little bit more than 1. So this is getting closer and closer and closer to having a radius of 1 as you go further and further up. It kind of looks like a really funky chimney. What I think of when I think about what this graph looks like is, what's that Dr. Seuss book? The one where he's like, the Dr. Seuss book where like all the places you'll go or whatever on the cover, and he's got like those weird like things that are like stripy around it. I feel like this kind of looks like that. Or not, whatever you think. Yeah, so domain range, kind of neat. Yeah, we should do more. Let's look at, do I have these other ones? No, not that one. That one's garbage. Let's look at these other ones. Sure. Oh, come on. So let's just talk about the domain range of these next couple functions. So let's say my function was f of x comma y equal to the square root of 16 minus x squared minus y squared. All right, domain. Our stuff has to be bigger than or equal to 0. I'm going to isolate the x squared plus y squared again. So 16 bigger than or equal to x squared plus y squared, or x squared plus y squared less than or equal to 16. So we are definitely, are we inside or outside this circle? Is the point 0, 0 satisfactory? Yeah, so we're inside the circle. And also including the circle, right? Because we definitely want the points that make it equal to 16, and 4, 0, which is on the circle, definitely satisfies this inequality. Okay, range. Well, I know that this is true. 16 minus x squared minus y squared has to be bigger than or equal to 0. Okay, here's my function. F of x, y equal to the square root of, I'm going to write it as 16 minus x squared plus y squared. And in addition to x squared plus y squared needing to be less than or equal to 16, it is also just true that something squared plus something else squared is always greater than or equal to 0. Has to be. Can't ever be negative, at least if you're using real numbers. So if I look at this, I'm thinking, okay, that part right there, the smallest x squared plus y squared can be is 0, which means I can get this to equal 4. So when x squared plus y squared equals 0, I get my function to equal the square root of 16 minus 0, which is 4. And then when x squared plus y squared are at their biggest, when x squared plus y squared equals 16, I get my function to equal the square root of 16 minus 16, which is 0. And I'm pretty confident that that's kind of the extremes. I can't make it any bigger. Right? There's no way to make 16 minus some stuff bigger than 16. I should say, there's no way to make 16 minus some stuff that's for sure positive, bigger than 16. And there's no way to make the insides any more smaller than 0 because 0 is the smallest it's allowed to be. So pretty confident here that the range is everything between and inclusive of 0 and 4. There's definitely a more algorithmic way of doing this particular one, but they really don't recommend it. Like you could totally be like, okay, I'm going to start with this. 0 less than or equal to x squared plus y squared less than or equal to 16, and then negate everything, which means you have to change the order of the inequality, and then add 16 to everything. And then take the square root of everything. So, oh yeah, you definitely get your function between 0 and 4. But it's not that this is wrong, this is totally right. I just feel like we can kind of think it out a little more easily. Be like, okay, well, this x squared plus y squared as at the smallest is 0. And if this is small, 16 minus it is going to be as big as possible. So when this is the smallest, 16 minus it is the biggest. And then when this is the biggest, 16 minus it is the smallest. But the biggest this is allowed to be because of the domain is 16. So one more time, there isn't like a tried and true process that always works. You kind of have to like feel around and see what works for you. Let's go one more example. Let's look at, again, a lot of these have an x squared plus y squared. I'm just gonna make one up. Let's say our f of x, y is equal to, we had that. Let's change it up. Let's do an x squared plus y squared minus 9. But let's do the natural log of x squared plus y squared minus 9. Sure, yeah, that's fine. Okay, domain. Domain at this point shouldn't be too bad. We know that x squared plus y squared minus 9 should be not greater than or equal to 0, but just greater than 0. Because we can't take the natural log of 0 or any log of 0. So our domain here is going to look like x squared plus y squared greater than 9. I'm going to draw the circle of radius 3, but dashed because we know we don't want to include the endpoints. And then we want everything outside of it because clearly the origin doesn't work. So we want all of this, everything outside of the circle. Okay. And then I guess we could write it the real way. The domain is the set containing x comma y, such that you could literally write it either way, x squared plus y squared minus 9 greater than 0, but it's often the standard way of saying I'm going to isolate x squared plus y squared. All right, range. So this is where it's useful to think about the range of your outer function. So if I was just looking at, say, f of, let's pick a different variable like f of, not z, James, pick something like q. Sure, if f of q is the natural log of q, the range here would be 0, negative infinity to infinity. right? This natural log function can go everywhere. As long as Q can go from 0 to infinity. So can I get this being super close to 0? Yeah, I can. Because x squared plus y squared minus 9 has to just be greater than 0. Well, essentially, I've got the same kind of condition here, right? Just like f of q being natural log of q, our domain is that the inside stuff is between 0 and infinity. I've got the same action here. My f of xy equal to the natural log of x squared plus y squared minus 9. It's certainly it's certainly true that x squared plus y squared minus 9 has to be greater than 0 and certainly going to get as large as we want it to get. So if that's the case, it looks like this function here can go all the way down to negative infinity and all the way up to positive infinity. So it looks like our range really is everything. Yeah. All right, I should stop talking because it's 3:01.